we'll introduce one more thing. We'll go into more detail next time. But we know energy is stored in fields. And so now we want to think about how energy is affecting matter. Or excuse me, how radiation, electromagnetic radiation is affecting matter. If I have an incoming radiative pulse again, and let me get some different colors here. So here's the radiative pulse, and here is the magnetic field pointing outward. If we could draw it better, let's draw it in this color. B is outward. And here's a charge. Let's just, again, make it a positive charge. We said this radiation comes in. Here's the direction of propagation. And the electric field is pointing upward. And so there's going to be an electric force upward, right? So we just got done talking about. If there's a force on the charge, what does it do? It accelerates. If the charge accelerates, what does it do? It accelerates, of course, but if you have an accelerating charge, what do accelerating charges do? Give off radiation. So this charge itself is going to give off radiation, which we'll just call re-radiation. Okay? Let's think about, now, let's imagine, just for a second here, we have a positive charge that gets accelerated upward, right? So that's the direction of acceleration for this positive charge. Here's my initial radiative field. And then I'm going to look somewhere down here at, say, location A. Well, at location A is upward. This is a positive charge. What's going to be the direction of the electric field due to the accelerated charge? What's going to be the direction of the re-radiative electric field when it reaches location A? Why down? It's opposite, right? Negative Q times A perpendicular is the direction, is how we get the direction. So we draw the R vector pointing from the charge to location A. And we say, okay, this acceleration, that is the perpendicular component. So when the radiation reaches this point, this E, call it E re-rad, just to make it different, is pointing downward. It's negative times this positive charge times A perpendicular, so it's going to be downward. Is that all we have? Is that the only field that we have here? We still have the original pulse. Somewhere back here we had some light source. So a flashlight, for example. We turn it on real quick, gives off a pulse of radiation, causes this charge to accelerate, and this pulse still travels along, and so we still have the re-radiation. So when I calculate the net electric field, it's going to be affected by this re-radiation, right? It's going to be smaller. So that's going to be E net. Here's a question for you, which you can think about for next time. We can talk about it more next time. Let's do it this way. Here is, all right, let me just make the light bulb burn for a second. We all can see the light bulb, right? We all can see it lit up. Why can't you see it now? There's stuff in the way. Okay, there's stuff in the way. There's light being blocked, light being absorbed, something like that, right? Ah, the superposition principle. Someone said the magic word. The superposition principle says that you have to have the original electric field and the new electric field and add them up and get a net electric field, right? The original electric field doesn't go away. We still have it, just like we had the original electric field if I were to add the electric field due to two charges, Q1 and Q2. I have to find E net over here by looking at E1 pointing that way, and E2, well, also pointing that way. The second charge doesn't somehow absorb or block the electric field from the first charge. It's just that we have both, and we have to take both seriously when we're applying the superposition principle. So we're going to use that next time to talk about various effects of light on matter. So we'll pick that up on Friday.